right, today we are diving into one of the most famous and, honestly, most misunderstood ideas in all of physics, the Heisenberg uncertainty principle. So let me start by asking you a question that really gets to the very heart of quantum mechanics. Is it even possible to know a particle's exact position and its exact momentum at the very same time? To get to the bottom of that, we're going to take a little journey. We'll start by busting a common myth, then get to the deeper reality, check out the great debates it caused, and see why it's so important today. Okay, first things first. We've got to tackle the biggest misconception out there. Most people think the uncertainty principle is just about us being clumsy measurers. You've probably heard this one before, right? The idea is, to see a tiny little electron, you have to bounce something off of it, like a particle of light. But in doing that, you inevitably knock the electron off course. So the very act of looking at it changes where it's going. And yeah, that kind of makes sense. It's a neat little trade-off. But here's the thing. While this observer effect is totally real, it's not the main event. It's a nice illustration, but it misses the entire mind-bending point. And this, right here, is the absolute key takeaway. The observer effect is about our tools getting in the way. The uncertainty principle says that even with perfect imaginary tools, there is a built-in, unavoidable fuzziness to the universe itself. The particle didn't have a precise position and momentum to begin with. So if it's not a measurement problem, what in the world is it? Well, this fuzziness isn't a bug in the system. It's a feature. It's a fundamental law of nature, something Werner Heisenberg first put into words way back in 1927. This is a tough one to wrap your head around, but uncertainty isn't about what we don't know. It's about a hard limit on what the universe allows to be known, all at once. And here it is, the principle in all its mathematical glory. Now don't let the symbols scare you. All this equation is really saying is that the fuzziness in position times the fuzziness in momentum has to be greater than or equal to some ridiculously tiny number. It can never be zero. That number on the right comes from something called the Planck constant, which you can just think of as the basic unit of weirdness in the quantum world. To put it simply, the more you nail down a particle's position, the more its momentum spreads out into a range of possibilities. And the more you zero in on its momentum, the less you know about where it is. They're locked in this cosmic seesaw, forever. But why? Why does this limit exist? Why does the universe have this rule? Well, the answer, and this is the real aha moment, lies in the deeply weird identity of every single thing in the cosmos. It all comes down to something called wave-particle duality. Turns out every single object, from a tiny electron all the way up to you and me, has a wave nature. And that's where this whole trade-off is born. The best way to get a feel for this is to stop thinking about particles for a second and just think about sound. Imagine a perfect single note being played on a violin. You know its frequency, its pitch, with incredible precision. But can you point to a single instant and say, that's where the note is? No, of course not. The note exists over a stretch of time. And that's exactly what's happening with a quantum particle. If a particle has a perfectly known momentum, its wave is like that perfect, unending violin note. It's just spread out everywhere. Its position is completely uncertain. So what if you want the opposite? What if you want a short, sharp sound, like a single clap? To create that localized sound, you actually have to smash together a whole bunch of different sound waves with different frequencies. And it's the exact same for a particle. To pin down its location, you have to build a wave packet out of many different momentum waves. The result? A precise position, but now its momentum is a fuzzy mix. It's just the nature of waves. Now, as you can imagine, this idea that reality itself is fundamentally fuzzy and based on probabilities did not sit well with everyone. In fact, it kicked off one of the greatest intellectual showdowns in the history of science. For years, at the center of the ring, you had two titans of physics, Albert Einstein versus Niels Bohr, going head-to-head over the very meaning of reality, with the uncertainty principle right in the middle of it all. Einstein just could not accept it. He famously said things like, God does not play dice. He felt that deep down there had to be a hidden, definite reality. For him, the moon has a real position even when no one's looking, and a tiny little particle should be no different. So he came up with this incredibly clever thought experiment to try and poke a hole in the theory. The idea was simple. You weigh a box full of light, let one photon out at a precise time, and then weigh it again. The change in weight tells you the photon's energy. So boom, you know the exact time and the exact energy. It seemed like a foolproof loophole. But Niels Bohr was a special kind of genius. They say he was up all night puzzling over it, and then he found the answer. And this is the absolute best part. He used Einstein's own masterpiece, the theory of general relativity, against him. Bohr realized that in order to weigh the box itself has to move a little bit, which creates an uncertainty in its position. And according to general relativity, that uncertainty in position actually creates an uncertainty in the flow of time itself. The principle was saved. So, okay, why should we care about some old debate between physicists from 100 years ago? What does all this fuzziness mean for us today? Well, it turns out this isn't just some weird footnote in a textbook. It's the rule that literally holds our universe together. It's the reason atoms are stable, the reason electrons don't just spiral down into the nucleus and destroy everything. And we use it all the time. It explains why some exotic particles created in accelerators don't have a single sharp mass. It's essential for designing the semiconductors in your phone, for understanding chemical reactions, and it even sets the ultimate noise limit on how well our most sensitive instruments can detect things like gravitational waves. So we started with a simple myth about measurement, and we ended up at a fundamental truth about the cosmos, that at its deepest level, reality is a game of probabilities, not certainties. And that leaves you with a final thought, doesn't it? If something as basic as where something is and where it's going can't be known for sure, what other things we take for granted might just be beautiful, fuzzy illusions?